Next question is 75. It is from aldehyde, ketone and carboxylic acid. It is regarding the correct order of the acid strength of a 4 given acids such as methanoic acid, ethanoic acid, 2-methyl propanoic acid and 2,2-dimethyl propanoic acid. 2,2-dimethyl propanoic acid. The number of alkyl groups are increasing. Okay, number of methyl groups are increasing. We know that the strength of a carboxylic acid may increase or decrease depending upon the electron withdrawing or electron releasing ability of the substituted groups. If you consider the change from HCOH to CS3COH, we know that all the groups which pushes electron towards the carboxyl group will increase the electron cloud density around the carboxyl group and thereby diminishing the tendency of the carboxyl group to ionize and release proton, because there the electron cloud density is increasing. So it will be more and more difficult for a proton to be released. For a hydrogen atom to release as a proton and leave away will become more and more difficult when the electron cloud density around the carboxyl group is increased by electron pushing groups. Okay, electron pushing groups are called plus inductive groups. We know that alkyl groups are generally electron pushing groups. Methyl group is in plus I group. Here what happens? When HCOOH changes to C3COOH, H is replaced by CS3 group. CS3 group is more electron pushing than H. So the tendency of acetic acid to ionize will be less than that of formic acid. Naturally, formic acid will be more acidic than acetic acid. Now we have substituted one more hydrogen in H using methyl group, isn't it? So what happened? The electron releasing tendency of the alkyl group increases even more, and so the proton releasing tendency of the COH group still diminishes in 2-methyl propanoic acid. If you introduce one more methyl group and convert this to 2,2-dimethyl propanoic acid, what happens? The electron releasing tendency of the alkyl part even more increased, and so the proton releasing tendency of the COH group is that much decreased, making it even less acidic. So we can say there is a gradual decrease in the acid strength from HCOOH through CS3COOH through CS3 twice CHCOOH and CS3 thrice CCOOH. Okay, so this is the what is written here will be the correct order of the acid strength for these 4 acids, and that option is option 4. For question number 75, the correct option is 4. Okay. Now the 76th question. See, it is from Basic Principles of Organic Chemistry, the detection of elements in organic compounds. Here, see what is and it is asking which does not belongs to the Lassaine's method of detecting element. That's the question's implication. See, what is Lassaine's test? What we do for Lassaine's experimentation? See, we take few crystals of the organic compound or 1 or 2 drops of the organic compound in an ignition tube, small ignition tube made of thin glass, and add some excess of metallic sodium into it, insert both together, and then heat it in a Bunsen flame until it fuses together and turns red hot. Once it is red hot, you plunge it in some water taken in a mortar and grind it, whereby the tube crushes, breaks, and the contents start dissolving in the small amount of water taken in that mortar. You grind them together and after cooling filter the solution, and this filtrate is used for experimenting with the Lassine solution. Okay, that is called Lassine solution, with which you perform several experiments. For example, if the organic compound always contain carbon. If it contains nitrogen also, this test solution, Lazine solution would contain NaCN, sodium cyanide, formed by the combination of Na plus C plus N, NaCN. So the solution would contain cyanide ion. And if you test cyanide ion with suitable reagents and find its presence to be there, you can be sure that the organic compound to contain nitrogen. Okay. Then again, if the organic compound contains sulfur, that will combine with the sodium. Here carbon is not involved. Sodium sulfide is formed, and if you test for sulfide ion in the Lazine test solution, then if it is found positive, that means the organic compound contains sulfur. Again, if the organic compound contains any halogen like chlorine, bromine or iodine, it combines with the sodium, forming sodium halide. And a test for halide, either chloride or bromide or iodide, verified through proper experiment, it confirms that the organic compound contains that corresponding halogen. Okay, hope you understood that. But so all these three are based on Lazine's experimentation. But this, where the organic compound is strongly heated with the pellets of cupric oxide, whereby cupric oxide get reduced to copper and the carbon in the organic compound is oxidized to carbon dioxide. That carbon dioxide's presence can be detected by using lime water, which turns milky. So if that happens, we are sure that the organic compound, that compound contain carbon, okay, then it can be an organic compound, isn't it? That does not belong to the Lazine's test. So for this question asks us to identify which is the test that does not belong to the Lazine's mode. So answer will be 1 for question number 76. Okay. The next question. It is from organic chemistry. Here it is asked how many possible isomers the structure can produce, including stereoisomers, upon monochlorination of this compound. What is this compound? It is 2-methyl butane, isn't it? 2-methyl butane, or it is having the common name isopentane. To understand how many structural isomers are possible, we have to number the carbon atoms in this compound or distinguish the carbon atoms based on their similarity and dissimilarity. We are not numbering to name it, but numbering to identify the different type of carbon atoms in it. Like this. This is 1. This is also 1 because they are identical. Structurally, they are identical. Hope you understood that. Now, this is 2, this is 3, and this is 4. Okay. What do I imply? See, upon monochlorination on this carbon or this carbon, you get one structural isomer. Upon monochlorination here instead, you get the second type. Upon monochlorination here, you get the third type, and upon monochlorination here, you get the fourth type. They are position isomers, isn't it? Here we don't have to consider the chain isomers because the chain is provided in the question. You are not supposed to alter that chain. So retaining this chain as such, how many different structural isomers, which are nothing but the position isomers upon monochlorination of this compound, we have to verify. So we have 1 upon monochlorination of either of this carbon, second upon monochlorination of this carbon, third upon monochlorination, 4. So 4. Now we have to verify how many optical isomers are resulted during this process. We'll check. Look here. Suppose you monochlorinate here or here. Will that carbon turns chiral or optically active with the 4 different attachments? No. Because it becomes ClCH2. ClCH2 means still it is having 2 hydrogen atoms on the same carbon. So it will not turn chiral. It continues to remain achiral, means optically inactive. It is not a stereocenter. But you have to verify the neighboring atom status also here. Upon monochlorination here, what happens to this carbon? You must think. What happened? Listen. Presently, it is not chiral or optically active or a stereocarbon. It is not a stereocarbon. Why? It is having two methyl group attached. So only when all the four groups are different, it can be optically active, isn't it? So presently it is not so. But upon conversion this to CH2Cl or ClCH2, what happened? All the four carbon attached to that carbon, this carbon, not this carbon. This carbon become different, and so this carbon turns out to be a stereocarbon, isn't it? Upon chlorination here, change is here. Hope you understood that. So this carbon turns stereocarbon, and so we have dextro-levo pairs, DL pair is resulted. We have already counted 4, no? So you need add one more only. Don't add 2 because 1 is already counted in this 4. So there one more you will have. So you have to add one more because upon monochlorination here, this turned active. So one more is added. Now think about second case. Replace this hydrogen by chlorine. In the second carbon itself, you are replacing the hydrogen by chlorine. Will that result in optical activity? We will verify. See, upon monochlorination here, that carbon will not turn stereocenter because still it is having two identical groups. This upon chlorination here, this carbon also will not turn optically active, very apparently. Nor this carbon will turn optically active, nor this. So monochlorination here doesn't bring out any new isomer. Okay. Now think about this carbon. If you replace one hydrogen here by chlorine, what happened? All the four groups or all the four attachment on that carbon happens to be different. What are they? One is an isopropyl group, other is an H, other is a Cl, other is a CS3. All the four groups are different now. If you replace one of the hydrogen with a chlorine here, this carbon would turn optical active. I didn't mean both together stand, even though in one case this turned, in the other case this turned stereocenter. Whenever a new stereocenter is generated, you have to add one because you are having DL pair, one already counted, so you can count one more only. Okay, one more only. So here you have one more new compound. Then last case here. Suppose you replace that one of the hydrogen by chlorine, it turns out to be CH2Cl. That carbon itself won't turn active because CH2Cl means two hydrogen atoms are there. So it cannot turn stereocenter. Nor it will convert this CH2 optically active, nor this, nor neither of this. So there also there is no effect. So our number of isomers is limited to be 6 only, including both the structural isomers and stereoisomers. So the answer for this question is 1. Among the given options, 6 is option 1. So for this question, our answer is 1 because it produces 6 isomers, including both the structural and stereoisomers. Hope you follow that. Okay. The next question, it is from biomolecule. See, it is like this. Question number 78. Sugar exists. And they have provided 4 features of that. What are they? Found in honey. First suggestion. Yeah. Honey contains both fructose, mainly fructose, and glucose. So, found in honey tells you that it can mainly be fructose or glucose, but not yet confirmed which it is. Is a keto sugar. Yeah. Then it must be fructose because we know glucose is a aldose sugar. So by second suggestion, we almost concluded that it is fructose. Then X is in alpha beta anomeric form. That is also valid for both the glucose and fructose. Both X's as anomeric alpha and beta form. Okay. Then D is levorotatory. By that we doubly confirmed that it is fructose because we know Glucose as well as sucrose are dextrorotatory, whereas only fructose is levorotatory. That's why it is also known as levulose. So D levorotatory confirms that it is fructose. So our answer among the given option 3, D fructose is our answer. Third option is the valid answer here. Okay. The next question 79. Dalton's atomic theory could not explain. This question is from Basic Concepts of Chemistry. Okay. See, we know Dalton's atomic theory is based on masses of reactants and products. Okay. Whereas law of combining volume of gases, which is here expressed as law of gaseous volume. Law of combining volumes of gases proposed by Gay-Lussac is regarding the volumes of reactants and the products, not regarding their masses. What the law states there, according to Gay-Lussac's law of combining volume, there exists a simple ratio among the volumes of reactants and products in a gaseous reaction at a fixed temperature and pressure. Okay, whereas law of conservation of mass talks about the equality of the total mass of the reactants and products formed during a chemical reaction, whereas law of constant composition says that the same compound always contains the same elements combined in the same fixed proportion by mass, whereas law of multiple proportion says that when two elements combine to form more than one compound, the ratio of mass of the one of the element that combines with the fixed mass of the other bears a simple ratio. So this law are based on masses. These three laws can be applied to any state of matter, whereas this law is exclusively for gases. These three laws, 2, 3 and 4, can be explained based on Dalton's atomic theory. Because Dalton's atomic theory as well as these three laws are based on the masses of reactants and products in a reaction. Okay. Whereas law of combining volumes of gases, which is exclusively applicable to gases only, is based on volumes of the gases. Since Dalton's atomic theory does not relate mass with the volume, it could not explain law of combining volumes of gases. That could be done by another gaseous law, which is Avogadro's law. For this question, our answer is Dalton's atomic theory could not explain law of gaseous volume. That is option 1 is our answer for this question. Okay. The next question is from equilibrium. Question number 80. N2 gas plus O2 gas reversibly giving to NO gas. Semicolon delta H is plus 180.7 kilojoule per mole. See, this here the product formation NO can be enhanced by. That's the implication of the question. I haven't written that here. You have to produce more NO, and which all of the following condition would favor the production of NO? That's the implication of the question. A, at a higher temperature. B, at a lower temperature. C, higher concentration of N2. D, higher concentration of O2. These are the 4 statements given. You have to choose which are correct from these 4 options. C, this reaction N2 plus O2 giving 2NO is highly endothermic. Delta H is plus 180.7 kilojoule per mole. We know that in atmosphere, N2 and O2 combine forming NO during lightning where huge amount of heat is generated. So that suggests that this is an endothermic process. Okay. So we know that any endothermic process is favored by high temperature. Okay. So among these statements, A is a correct statement. At a high temperature, the production of NO will be enhanced. Naturally, B will be low because it suggests at a low temperature, because it is not an exothermic process. That's the answer. So B cannot be an option here. Then higher concentration of N2. Yeah. See, for gaseous reaction, a high concentration means high partial pressure of N2. So we know when the concentration or partial pressures of the reactants are enhanced, the forward reaction is favored by as per Le Chatelet principle. So high concentration of N2 as well as high concentration of O2, which is the other reactant. So higher concentration of N2 as well as high concentration of O2 both would favor the forward reaction, which is the production of NO. So this statement as well as this statement are true here. To conclude, statements A, C and D are correct here, isn't it? A, C and D are correct here, which is option 1. So for question number 80, our answer is option 1. Okay. Next question is from P block element regarding noble gas compounds. Okay. Xenon compounds. See, it is a matrix type. Match the following type. You have to match the appropriate ones. The first one given is XeO3, xenon trioxide. You have to identify its hybridization and structure. Okay. So we start like this. Xenon XeO3. The first thing you have to do, if you are already not familiar with what you have to do, first you draw a rough diagram to identify how many bonds it is forming. I have drawn it as Xe and 3 doubly bonded oxygen atom. Means the central xenon has to form 6 bonds. To form 6 bonds, there must be 6 unpaired electrons. Okay. And we know, being a noble gas atom, xenon doesn't have any unpaired electron. Its electronic configuration in the ground, valence electronic configuration in the ground state is 5x2, 5p3. No unpaired electron is there, isn't it? So, to avoid 6 unpaired electron, 3 pairs of electron must get unpaired by making use of 5d orbital, vacant 5d orbitals. So, 3 of the electron among them get promoted like this to 3 vacant d orbital. So there are 6 unpaired electrons as well as 1 lone pair. Now it must undergo suitable hybridization so that the resulted molecule have minimum repulsion, maximum stability, etc. See, here we have to remember one more thing. All the sigma bonding electron containing orbital must be involved in the hybridization. All the lone pair of electron in the valence shell also must be involved in hybridization. Okay. Here we know this will form a sigma bond. But one more thing, pi bonding electron containing orbital should not be hybridized. Pi bonding electron containing orbital should not be hybridized. So, see, this is sigma. Since this form one sigma bond, it is hybridized. Another sigma bond hybridized. Another sigma bond hybridized. This is kept as such. Lone pair, it is lone pair, so that should also be hybridized. Whereas 3 are kept aside for pi bond formation. So they should not be hybridized. It's the law in how things happen in nature. Okay. So we have sp3 hybridization here. We have sp3 hybridization here. And we know in sp3 hybridization, the regular structure is tetrahedral. Regular structure is tetrahedral. Okay. Then the regular structure is tetrahedral. And see, among these 4 tetrahedral orbital, 3 will be used for sigma bonding with the oxygen. This will be forming 1 sigma bond. This will be forming 1 sigma bond. This will be forming 1 sigma bond with separately with the 3 oxygen atom. And 1 will remain as a lone pair. 1 will remain as a lone pair. 1 orbital will be having 1 lone pair, which is also hybridized. Now, 3 unpaired electrons present in the unhybridized orbital are used for secondary bonds with distorted tetrahedral structure. And what the shape? Well, you consider the shape, you ignore the orbital containing lone pair. The remaining part alone is considered while we express the shape. It is called a trigonal pyramidal. Base is triangular. So trigonal pyramidal. Pyramidal or simply pyramidal or trigonal pyramidal is the exact word. So we got the details regarding XeO3 so far. Okay, now we consider the next compound. Next compound is XeF2. Okay, first you draw the symbol picture. Here we see it requires 2 sigma bond or 2 bonds, so it requires 2 unpaired electron. It requires. So only one pair of electron need get unpaired, producing 2 unpaired electron. Okay, like this. And for the hybridization, all this must be involved because bonding orbital should be hybridized. Lone pair containing orbital in the valence shell also must be hybridized. So the possible hybridization is sp3d. sp3d hybridization. And what is the details regarding sp3 central of a molecule in which the central atom is sp3d hybridized, XeF2. Look here. For sp3d hybridization, the regular structure is trigonal bipyramidal. That is 3 orbital directed to the 3 equatorial position of a regular triangle, one above the other below, one above the other below. So 3 equatorial, 2 axial, like that the 5 orbitals are distributed. In this particular case, the 2 sigma bonds are formed along the axis, whereas the 2 sigma bonds are formed along the axis. This is a sigma bond, this is a sigma bond, these 3 are 3 lone pairs. So lone pairs are directed towards the 3 corners of a regular triangle, and 2 sigma bonds are located axially. So our XeF2 sp3d hybridization structure trigonal bipyramidal, and shape which excludes the lone pairs of electrons involved is linear. The shape is linear. You must also remember structure is also called electron pair geometry because it involves or it considers also the valential electron pairs even when it is not involved in bonding. So structure is more scientifically called electron pair geometry, whereas shape, which ignores the lone pairs of electrons in the valence orbital, it is called molecular geometry. Because it is not bothered about the lone pairs of electrons in the valence shell, it is bothered only about the location of the atoms in the molecule, or it is concerned only about the apparent structure, which is shape. So remember here in this particular case, structure or electron pair geometry is trigonal bipyramidal, whereas shape or molecular geometry is linear. Hope you understood that. We will proceed to the third case. The next one, it is XeOFO. So immediately we draw the rough diagram. There we see 4 single bond, 1 double bond. Means it has to form 2, 4, 6 bonds. Means there must be 6 unpaired electron. So 6 to generate 6 unpaired electron, 3 pairs of electron must get unpaired as here. Look, 1, 1, 1, 2, 1, 1, 1. Now again consider. Here only 5 bonds are sigma bonds, 1 is a pi bond. Agreed. So one orbital containing a single electron must be exempted from being hybridized. That one orbital should not get hybridized. See, this has to this lone pair and 2 more lone electron. All these get hybridized. That is sp3d2 hybridization, leaving behind one unhybridized orbital with a lone electron. So the hybridization is sp3d2. What is the regular structure for sp3d2? It is octahedral. Octahedral is actually square bipyramidal is actually called octahedral. Square bipyramidal. It is rarely known by that name. It is mostly called octahedral. How? Look here. Xenon. 4 sigma bond with the 4 fluorine atom. 1, 2, 3, 4. Along the 4 equatorial, you may call, even though it is not correctly strict to classify orbitals as equatorial and axial in octahedral structure. You know why? See, you can keep 2 bonds above and below octahedral, in octahedral structure, and 4 remaining in the 4 axial position. You can make any pair the axial so that the other 4 will be equatorial. So any pair, opposite pair can be made axial so that the other 4 become equatorial. So axial equatorial distinction is not there in true octahedral geometry. Still, for the convenience, we may say 4 equatorial bonds are formed by xenon with the fluorine, and 1 axial bonding is as double bond with 1 oxygen atom. Okay, and 1 lone pair is remaining. That will be in the other axial position shown downward here. Downward, upward, etc. are just pictorial. There is no meaning actually. If one is above, the other will be below. That's all. So this is the appearance of XeF4O molecule or XeOFO molecule. Okay, so what is its XeOFO sp3d2 hybridization? Its structure is distorted octahedral, distorted due to the presence of this lone pair, distorted octahedral, and shape, you simply ignore this so that it is square pyramidal. If you avoid this, it is square pyramidal. The Egyptian pyramids are actually square pyramidal, isn't it? So that shape. So we have mentioned C also. In one more case is remaining, which is XeF6. Okay. Now we proceed to the last case, D, XeF6. See, in the rough structure, we see that there are 6 bonds, so there must be 6 unpaired electrons. As in the previous case, or in the previous case also, there were 6 unpaired electrons. So 3 get unpaired, so that there are 6 unpaired electrons and 1 lone pair. Here, since all are formed, no pi bonds are involved in this structure, so all these single electron must be hybridized. So we have sp3d3 hybridization. sp3d3 hybridization. What about the structure then? See, sp3d hybridization, trigonal bipyramidal. What is sp3d2 hybridization? Square bipyramidal. Now sp3d3 hybridization, pentagon bipyramidal. In the regular sequence, trigonal bipyramidal, square bipyramidal, which is octahedral, and pentagonal bipyramidal. Things are happening in a systematic way. So we expect a pentagon bipyramid. Here clearly there are axial orbitals and equatorial orbitals. 5 orbitals, hybridized orbitals are equatorial and towards the corners of a pentagon, and 2 are axial. And making use of 6 orbitals, it form 6 bonds with the fluorine, and 1 lone pair where it must be located in the axial or in the equatorial. Nobody can be sure about that. Only by studying the original molecule, it has been found out that that lone pair occupy one of the equatorial position and not axial position. It has been proven experimentally that when it occupies equatorial position and not axial position, the structure gets better stability. That's the reason the molecule decides, or the nature decides where it must be located, not we. We only study what has nature chosen. Okay, so this is the thing. So details regarding XeF6. XeF6 sp3d3 hybridization. Structure distorted pentagonal bipyramidal due to, why distorted? Due to the presence of lone pair in the structure. Whenever lone pairs are there, there is always the possibility of deformation. Okay, so or deformation or distortion. So distorted pentagonal bipyramidal. What is shape? That is when lone pair is ignored. Then it is almost like a distorted octahedral or distorted square pyramidal. No, we don't say distorted square bipyramidal. It is rarely used. Say distorted octahedral. So distorted square, I have written there wrongly. Distorted octahedral is the common usage of the word. Distorted octahedral. Okay, so we have given explanation for the whole. So now we conclude. Okay, our conclusion. Look here, with four compounds given: XeO3, XeF2, XeOFO, XeF6, ABCD, and the appropriate or correct matching XeO3 to given option 2 sp3 pyramidal. Agreed. XeO3. XeF2 1 sp3d linear. XeOFO option 4 or option or cross matching 4 sp3d2 square pyramidal. XeF6 3 sp3d3 distorted octahedral. Actually here they have given the shapes or molecular geometry and not the structure or electron pair geometry. They have correctly done because in all cases they have taken only shape, not the structures. And such a combination of options is given in 2. So our answer for this particular question is 2. The next question, question number 82. It can be said to be from chapter solution or the practical, because there we discuss some solutions. So either way, okay. What is it? It is a cross-matching type question. You are in the first column, you have humidity, alloy, amalgam, smoke, and you have to cross-match it with which type of class it is, like solid in solid, liquid in solid, like that. Let's verify. So humidity, we know humidity is moisture in air, no, isn't it? Humidity is moisture in air. So humidity is moisture in air, isn't it? So it is liquid in gas. Humidity is liquid in gas. Agreed. Now alloy is a solution of two solids, no? One solid dispersed in the other solid. So it is solid in solid. Amalgam. Amalgam is obtained by stirring, adding mercury to certain metals, and the resultant mixture will be a solid. So you can say it is liquid in solid. Amalgam impregnated or metal impregnated with amalgam or mercury. So it is liquid in solid, amalgam. And smoke, we know, solid carbon particles in air or carbon dioxide, solid carbon particle in carbon dioxide or air, whatever it is. So smoke, solid in gas, solid in gas, isn't it? So 2, 1, 4, 3, such a combination option is given. 3 is the answer here. Answer is 3 here. Okay. Question number 83. It is from atomic structure. You are given two species, He plus and Li2 plus, and you have to find their energy, electron in the single electron in He plus and Li2 plus. You have to find out the energies as well as the radius of the single shell in which the electron is occupied. This is the first shell. Okay. See, we have directly applied the studied equation. He plus minus 2.18 into 10 to the power of minus 18 Z square by N square. For helium, nuclear charge Z is 2. So for helium plus the charge is 2, that is Z is 2 and shell number is 1. So substituting 2.18 into 10 to the minus 18 Z square by N square is minus 2.18 into 10 to the minus 18, 2 square by 1 square. Upon simplification gives you minus 8.17 into 10 to the power of minus 18 joule for He plus. Now it's a radius. Here the equation we have to study is 5.29 into 10 to the power minus 11 n square by z meter. The unit is in this particular constant. For this particular constant, the unit is meter. And now you substitute 5.29 into 10 to the power minus 11 n. N is first shell, because when there is only one electron, it will occupy n is equal to 1. So 1 square by z for He plus 2, isn't it? So simplification gives you 2.6 into 2.645 into 10 to the minus 11 meter. But the options given is a picometer. To convert into picometer, you have to multiply it with 10 to the power 12. You have to multiply it with 10 to the power 12. Then you get 26.45 picometer. Now similar things apply to Li2 plus. First energy, minus 2.18 into 10 to the minus 18 z square by n square. Here z is for helium, it is 3, so 3 square. Shell is again 1, because when there is only one electron, it will always occupy first shell, 1 square. Then you get a minus 19.62 into 10 to the minus 18 joule. And to find the radius, 5.29 into 10 to the minus 11 n square by z. Here n is again 1 and z is 3, 1 square by 3. So you get a 1.763 into 10 to the minus 11, multiply with 10 to the 12, you get a 17.63. And these set of answers are provided for option 2 is your answer here. Question number 83, answer is 2. The 84th question, it is from periodic classification of elements. See here, 5 elements are given with their valence configuration. From this valence electronic configuration, you have to identify them to be the main block element or not. Main block can be either S block element or P block element. If it is an S block element, or if it is a P block element, it is a main block element. If it is a D block element, or if it is a F block element, it should not be treated as a main block element. Let's quickly verify. Ne3S1, it is an alkali metal, S block, so main block, isn't it? S block is a main block. So this is main block element. 3D34S1, that's a D block element, so not a main block element. 4D10, 5S2, 5P3, it is a P block element, isn't it? So main block element. 3D10, 4S1, we know that it is the last transition metal, so it is not a main block metal. 5F0, 6D2, 7S2. It is neither S block nor P block. Its configuration says it is a D block element, but actually it is included in the F block if you verify in the periodic table. Anyhow, it is not a P block element or S block element. It is not a main block element. So we have only A and C as the answer, isn't it? A and C. Option 3 is the answer here. Option 3 is the answer here. Now, question number 85, it is from thermodynamics. It is a diagram based question. See, they have given in the question a thermodynamical equation. C solid plus 2H2 gas giving CH4 gas, delta H is minus 74.8 kilojoule per mole. And after giving a set of diagrams, they are asked which one is the correct representation for this situation. See, you have to remember this. Here, since the reaction is exothermic, there is a decrease in the energy content of the product compared to that of the reactant. So, reactant must be at a higher energy level and product must be at a lower energy level when the reaction progresses. Agreed. Now, again, this 74.8 or minus 74.8 is the energy difference between the reactant and the product. So, it is the energy difference between these two states, not between this and this, nor between this and this. So, only that diagram in which this energy difference is shown in between these 2 points should be selected. If you verify, I haven't drawn other options. Only this will correspond to that. Don't worry about the negative sign here. they simply suggested the magnitude of energy difference between these two. When it is up, it is plus 74.8. When it is down, it is minus 74.8. So they have avoided the sign there. So among the given option, which one is this option? Option 2 is the correct answer for question number 85. Okay. The next question number 86. This question can be said to be from haloalkene, or hydrocarbon, or amine. Can be classified with any of these because the reactions involved belongs to different chapters. Okay. See what happens here. It is pentene derivative. 1-methyl pent 1-ene. Here 3 reagents are suggested to be used one by one. First is HBr with the benzoyl peroxide. We know that HBr, when used along with an organic peroxide with an alkene, antimarconic addition takes place due to Karash effect, and halogen goes to that carbon which contain more hydrogen. So what happens here? Here bromine comes over here, which already has one hydrogen. So at the first stage, this will be the product. Okay, antimarconic addition product you are getting here. Then what is the next reagent we are using? KCN. It converts, substitutes, nucleophilic substitution. Bromine is substituted by nitrile group, cyano group. You get this product. CN replaces Br. Okay, and finally we are reducing this with the sodium amalgam and ethanol, Mendes reduction. This reduction converts the nitrile group to an amino group. CN is converted to CH2NH2 by addition of hydrogen. So this will be the final product. As per the given options, 2 is the answer. So for this question, 86, 2 is the answer. The next question, it is from chemical bonding. See, here they have given set of compounds arranged in a decreasing order with respect to certain properties they have mentioned. So we have to verify which all are correct order, which all are incorrect with respect to the order. Okay. See, first one, H2O greater than NH3 greater than CHCl3. And that is with respect to dipole moment. See, that is correct. You know why? H2O dipole moment, it is in our textbook 1.85 dBi. NH3, that's also the 1.47 dBi. And chloroform, CHCl3, it is a low dipole moment of 1.08. So they are correctly arranged in the decreasing order of their dipole moment, H2O, NH3 and CHCl3. It is a correct arrangement. Now the next one. This is with respect to the number of lone pair of electron on the central atom. Here in all the 3 molecules, central atomic xenon. See the first compound XCF4. If you remember, in XCF4, look here, the structure is like this. 4 XCF bond and 2 lone pairs are there. sp3d2 hybridization. So it is having 2 lone pairs of electron. XCO3, you know, pyramidal with 1 lone pair. Okay. And XCF2, we know it is having 3 lone pairs. So actual order should have been XCF2, XCF4, XCO3 with respectively 3 lone pairs of electron, 2 lone pairs of electron and 1 lone pair of electron, whereas they have wrongly given XCF4 greater than XCO3 greater than XCF2. So B is incorrect. A is correct, B is incorrect. Next is bond length. They have given OH greater than CH greater than NO. Only those who are familiar with the bond length values, etc., can answer this question. Here, NO is having the highest bond length 136 pm, then CH 107, then OH 96. Here, some rough ideas we can gather. Here, since hydrogen is not involved, its bond length Na with Na and O is the highest. Then we have CH and OH. We know O is smaller than C. So CH bond will be slightly longer than OH bond. So even without making the values by heart, sometimes our assessment can be correct. So NO bond length greater than CH bond length greater than OH is the correct answer. Whereas they have given OH greater than CH greater than NO. So this is also wrong. And finally, they have given bond energy or bond enthalpy. N2 greater than O2 greater than H2. Actually, this is rather easy because even without knowing the bond enthalpy values of these three compounds, we can guess because the first one is triple bonded, second one is double bonded, N2 is triple bonded, O2 is double bonded, and H2 is single bonded. So bond enthalpy would be definitely decreasing in the order N2 greater than O2 greater than H2. The values are also available for us in the textbook. N2 946 kilojoule per mole, O2 498 kilojoule per mole, and H2 435.8 kilojoule per mole. So that is correct. So here we see only A and D are correct here. B and C are wrong here. A and D. 2 is the answer for this question. Question number 87, answer is 2. Okay. The next question number 88. Total number of possible isomers, both the structural as well as stereoisomers of cyclic ethers of molecular formula C4H8. See, this can be said to be from hydrocarbon chapter or ether or even from haloalkane and haloarine where we study stereoisomers. Okay, wherever it is. Personally, I felt that this is the most difficult problem in the whole of this examination. It involves much of imagination and there are large number of possible structures which a student may find very difficult to be solved in the limited stipulated time within a entrance examination hall. Anyhow, we will try to get them. See, C4H8O. Just a minute. C4H8O, the very formula suggests that it is having either a double bond or a ring. Why? C4, if it is saturated, would have H10. But here it is C4H10. It is not C4H10O, but C4H8O. So it must be a cyclic compound if it is not having a double bond. Okay. Then the first possible formula, this is the one. Cyclic ether in which oxygen is in the ring, part of the ring. And they have asked cyclic ethers. They have specifically asked. So this will be the first case to be considered. Okay. It is tetrahydrofuran, if you know. Okay. It can be also called oxacyclopentane. Oxacyclopentane means cyclopentane in which one of the CH2 is replaced by oxygen. Actually, it will be having infinite conformational isomers where the ring does not remain in a plane but in a flipped manner. So if we consider all those stereoisomers, the answer here would be infinite. So we come to the conclusion that they didn't consider conformational isomers possible for this one. For any of the compounds, they haven't considered conformational isomers because in that, if they have included that, it would become infinite. The answer would become infinite. So we start from oxacyclopentane. Now we go to oxacyclobutane with one methyl group as a side chain. Look here, it is a diamond-shaped etheric molecule with the extra CH3 either on the next carbon or on the rearmost carbon with respect to oxygen. One structure is this. Look here where CH3 is on the next carbon. See this carbon, when the methyl group occupy this carbon, you can say this carbon is a chiral carbon. And so the molecule has no plane of symmetry. So this compound will have dextro, it's a mirror image, non-impossible with itself. Its object form and mirror image form will not be superimposable to each other, and so it will have a pair of dextro and levo. Okay, so while we number, this is 1, this is 2 and 3 because it is having dextro and levo forms. Now we go to the other possibility where CH3 occupies the rear carbon like this. Okay, but here the molecule is having a plane of symmetry. And not only that, this is not chiral because with respect to this carbon and this carbon are identical. So this molecule does not have a plane of symmetry, has a plane of symmetry, this molecule, and so no optical isomerism. So unlike this case, here there is only one compound. Now we go to 3-ring structure. 5-ring structure we first considered, then 4-ring structure we considered. Now 3-ring structure like this oxacyclopropane with the 2 methyl groups. Okay, now think the possibility, the 2 methyl group on 2 different carbons, both occupying similar positions. See, look at the diagram, then you will understand. CH3 is shown with the dash wedge line. Okay, this molecule has a plane of symmetry. And so no optical isomerism. It has 2,3. Position 2,3 is occupied by methyl in a symmetrical manner, the cis type arrangement, and so it has no optical isomerism. The other arrangement is, look here, in one case the CH3 is above the ring and in the other carbon it is on below the ring. Okay, if you consider ring like this in a flattened manner, not in the plane of the board, but like this, in this structure you will see one CH3 is above the plane, the other CH3 is below the plane. It is the trans arrangement of the substituents and it has no plane of symmetry, so its mirror image will not be superimposable on this, and so it will have 2 forms. So far we have 1, 2 and 3, 4, 5, 6 and 7. The next one, both the methyl group on the same carbon, both the methyl in propyl, both the methyl on the same carbon. See, it has no plane of symmetry, it has plane of symmetry, no optical isomerism. So it is the 8th one, it has no optical isomer. So 8th one. The 9th one is, instead of having 2 CH3 separately, we can have one ethyl group, no? So upon this carbon, we have one H and one CH2 CH3. Upon the other carbon, it will be 2 hydrogen. So this carbon become optically active. The molecule has no plane of symmetry. It is, remember, it is oxacyclopropane with the ethyl substitution. So all the 4 carbons are considered now. Remember, it has no plane of symmetry, so it will have dextro and levo form, making a total what? Look, 1, 2 and 3, 4, 5, 6 and 7, 8, 9 and 10. There are 3 DL pairs, that itself make 6 and extra 4, making total 10 possibilities. Conformational isomerism totally ignored. Otherwise, as I told you, answer would have gone to infinity. Then, so that finishes the treatment. We have 10 possible structures. You may be easily guess that it is not that easy to answer in an entrance hall, especially when this mirror image visualization etc. are required, isn't it? Okay. Question number 89. See, here they have given A gas reversibly giving 2B gas for which it is mentioned in the question that rate constant for the backward reaction KB is equal to 2500 times the rate constant for the forward reaction. Okay, at 1000 Kelvin. Then you are asked to find out Kp, equilibrium constant with respect to the partial pressures. How we will proceed? Look here. A gas giving 2B gas. Here itself you can calculate delta N gas, 2 more gas molecule minus 1. 1 is delta N gas. Now Kb is equal to Ka into 2500 at 1000 Kelvin. But we know that equilibrium constant Kc is equal to Ka by Kb. Rate constant for the forward reaction divided by rate constant for the backward reaction, Ka by Kb. Ka you substitute as Ka itself, and instead of Kb you substitute 2500 Ka, means 1 by 2500. Let it be there. Now Kp we know Kc into RT to the power delta N. Okay, Kp is equal to Kc into RT to the power delta N. Kc is equal to 1 by 2500 into RT. R is 0.083 given in the question, and T also given in the question into 1000 whole to the power delta N1 is equal to 1000 into 0.083 is 83. 83 divided by 2500, 0.033 atm. You will get the answer as 0.033, and the answer given is 4. Option 4 is your answer for this question. Okay. Now we have the 90th question, the last question in the Neet question paper. It is from solution. Okay. What they discuss? Look, 5 moles of liquid X and 10 moles of liquid Y make a solution having a vapor pressure of 70 torr. The vapor pressure of pure X and Y are 63 torr and 78 torr respectively. Which of the following is true regarding the described solution? Up to that we will write as equations. See, listen here. Sum of, we have mixed 5 mole X and 10 mole Y. Okay. Then, also given P total of this mixture is 70 torr. We are also provided with the vapor pressure of pure X and pure Y. Pure X it is 63 torr and pure Y it is 78 torr. In that case, we can find the ideal total pressure. That is the total pressure if the mixture of solution were ideal. P ideal is equal to P0X into mole fraction of X plus P0Y into mole fraction of Y. That we can calculate because all the data required to calculate this is given. How? P0X is given 63 and the mole fraction of X 5 divided by 5 plus 10, 5 by 15 plus P0Y 78. Mole fraction of Y 10 by 15. Easy to calculate. 21 plus 52, 73. 73 torr. So, ideal pressure is 73, but actual pressure is 70. That is, there is a decrease in the total pressure. Means the mixture is showing negative deviation. It is not ideal. If it were ideal, this pressure would also have been 73. So, now we can answer which statement is true. The solution has a volume greater than the sum of individual volumes. No. See, if the solution were only if it is ideal upon mixing 10, whatever be the volume, 100 plus 200 gives 300. That happens only if the solution mix formed is ideal. If it is showing negative deviation, there will be a decrease in the total volume. If it is a positive deviation, total volume showing increase in the total volume. So here, since the deviation is negative, the solution has volume greater than the sum of, it is wrong. The volume of the mixed solution will be less. It will not be greater because it is not showing positive deviation, it is showing negative deviation. So the very first statement is wrong. Okay. Then 2. the solution shows positive deviation. No, we have mentioned it is showing negative deviation. No. 3, the solution shows negative deviation. That is correct. The solution is showing negative deviation. So 3 is correct. The solution is ideal. The solution is not ideal. We have seen that. Okay. So actually giving such combinations of option itself is not good. One suggests positive deviation, other suggests negative deviation, other suggesting ideal. Only one can be true. There is no confusing anything about it. So very straightforward. So our answer for this question is this, that 3. That is the true correct statement is the solution shows negative deviation. The solution shows negative deviation is the correct answer for this question. 9, the answer is 3. So if you look through the whole question paper, it is not much easy for the students to work out all the problems, all the logic, all the imagination within the stipulated time frame. So I say that this question paper is much above the standard, especially when compared with the previous exams, previous Neet exams. So I think they have planned to raise the level to that level which were there before the advent of COVID. So our preparations must be improved. We must be more serious about our preparation. Okay. So take care. Start preparing. Bye. Take care.